Hi guys, welcome to another video in the motion and forces topic. In this one we're going to focus on speed and velocity. Speed is a measure of how fast an object is traveling. It's a scalar quantity because it only has size. It doesn't include a direction, and that is going to be one of the key things that differentiates it from velocity. We measure speed in meters per second, which can be written in either of these forms, meters over seconds or meters often with a dot times seconds to the -1. So seconds to the -1 is the same as 1 over seconds, and that's why we use that notation. It's just scientific notation, which is quite common when we look at physics topics. The other, I guess, most common measure of speed would be kilometers per hour or kilometers hours to the -1. Speed is defined as the distance traveled per unit of time. So we can describe speed as how far something is going in a certain unit of time. To demonstrate that, a constant speed of 5 meters per second means that every second of that object's motion, it is traveling 5 meters. 5 meters in 1 second, 10 meters in 2 seconds, and so on. Now, when we're talking about speed, speed is a very general term, so we need to try and identify some of the different descriptors that we use when we're talking about speed, and one that we've looked at already is average speed. Average speed is something that we can calculate when we know that the speed is changing. So if you were to calculate the speed at which you covered the distance between your home and the school, for example, that may include a trip in a car or a bus where occasionally you might have been doing 60 or 70 kilometers an hour, perhaps 80, depending on where you've come from, and other times where maybe you're doing 40 in a school zone, or even when you were stationary at a traffic light. So when we know that the speed is constantly changing, it's useful for us to calculate an average speed. The average speed is simply taken by dividing the total distance traveled by the total time taken. And again, that's a calculation that we've done in the past. The units for speed depend on the units of distance and time. So if they are meters and seconds, then it's meters per second. And if they are kilometers and hours, then it's kilometers per hour, and so on. Now we can also calculate average speed from the gradient or slope of a distance time graph, and we'll have a look at graphing in a little bit more detail in a different video, not this one today. It's quite useful when you're doing physics calculations to set up a little triangle like this. The purpose of this triangle is that if you cover one of these, you can find the other two. So if we know, for example, that the average speed is equal to the distance over the time, then we can find the time by dividing the distance by the average speed, or we can even find the distance by multiplying the speed and the average speed and the time together. So if we look at a couple of examples, if we calculate the average speed of a car that travels a distance of 100 meters in 5 seconds, then the average speed is going to be equal to 100 meters divided by 5 seconds, which is equal to 20 meters per second. If we need to determine the distance that a runner would travel in 1 minute if they ran at 0.5 meters per second, then we rearrange our equation to give us the distance being equal to the speed average multiplied by the time. So if the average speed is 0.5 and they travel for 1 minute, notice that we have a minute and we have per second here. So this is going to be 60 seconds because 1 minute equals 60 seconds. Because we're multiplying these two together, we have a total of 30 meters. Make sure that your units match the quantity that you're looking at. In the third example, we have how long would it take? This is a time. A cyclist traveling at 2.5 meters per second to cycle 1,000 meters. Again, let's check the units are the same, meters and meters in this case, and you'll see that t is equal to distance divided by speed average. So if we use that, then we get 1,000 divided by 2.5, and that is going to be equal to I will do this in the calculator, so I'm not guessing, and we get a total of 400 seconds. And if I was to divide that by 60, then I would get 6 or 6.67 minutes. It's not necessary for you to change these units, but sometimes they make more sense when we change them, particularly if we have very large values. Now, another important qualifier of speed is instantaneous speed, where you've started to analyze your motion of for your particular sport, either yourself or the ball and how it's traveling, then it can become more important for us to start to identify exactly what is going on at any given instant. As I mentioned, if we're traveling on the way to and from school in a bus or a car, the speed is going to continue to change from moment to moment. Sometimes you will be traveling at 60 kilometers an hour, other times you'll be stationary at a traffic light. The speedometer in the car actually is a measure of instantaneous speed. Of course, it's not in meters per second, it's in kilometers an hour, but it gives you the same thing. It shows you how the speed is changing for each moment of your trip. Now we want to compare what we understand about speed with velocity. Velocity is speed. The important thing to remember about this is the two terms are interchangeable with one difference. Velocity is speed in a particular direction. So its magnitude is always the same, but it has a direction, and therefore that makes it a vector quantity, as vectors have both size or magnitude and direction. So velocity is always going to have the same units as speed, meters per second or kilometers per hour, and so on. When we're calculating the average velocity of an object, we do that in the same way as we do for the average speed, but the difference is that when we calculate average speed, we calculate distance divided by time. When we calculate average velocity, we calculate the displacement over time. This gives us some unusual things, such as if it takes 10 seconds to run around a circular track, and the circular track is 300 meters, and it takes 10 seconds to do that, which it obviously wouldn't. Let's make it say 30 seconds. Then we would be traveling at a speed, an average speed equal to distance over time, which is 300 over 30, 10 meters per second. Unfortunately, the average velocity, average, would be 0. And that's because the total displacement is 0, and therefore it doesn't matter what the time is going to be. Anything that trying to divide into 0 is just going to be 0. So this is where we need to be very careful when we're calculating our average velocities. But there's some ways of overcoming this and still making some of these values very relevant and very important. So let's have a look at a couple more. When an object is traveling 40 kilometers in 5 hours, could we analyze this motion in order to determine whether there were points where the instantaneous speed was greater than the average speed? Well, if you're going to answer a question like this, you need to think about what we talked about earlier. Firstly, we can calculate an average speed, a speed average, by dividing the distance by the time. If it's 40 kilometers and it's 5 hours, then its average speed is 8 kilometers per hour. Notice in this case, its average velocity is going to be exactly the same. We have no direction here. All we are told is how far it's gone and how long it took for that journey. So it is still going to be 8 kilometers per hour. We just don't have a direction. And if you don't have one, then you can't calculate it. So you just leave it in this term. The problem though is we've got to decide whether or not at any point it could have actually been above that. And hopefully the answer is obvious that yes, it could. Because if there are times when it's traveling at, say, 16 kilometers an hour, they will balance times when it's traveling at 0 kilometers an hour. That is, when it's stopped. And this is one of the limitations in trying to calculate average values, because sometimes they're not really very meaningful. All they do is give us an overall picture of a journey rather than a breakdown of exactly what is happening. But as we mentioned before, you can also use graphs to help you determine average velocities. So could we use the graph to determine the average velocity from 0 to 6 seconds for the graph shown here? Well, what you can see is that this particular object is scaled as position north. So from the 0 mark to the 6 second mark, which is here on the scale, the object has moved from 0 to 4 meters north. We'll change the color of that so it's a little easier for you to see. So therefore, the average velocity is displacement. Unfortunately, displacement, because d already means distance. So displacement, I probably should put that there for you, has the value s, which I know is going to confuse us with speed as well, but let's just stick with it for the time being. The total displacement is therefore 4 meters north divided by 6 seconds, which is 0.67 meters per second north. The important thing when we're looking at calculating our vector quantities is that we need to make sure that that direction where we have it is shown. Thanks for watching.